Let us begin somewhere familiar, somewhere you can touch. Imagine, if you will, the smooth surface of a wooden table beneath your fingertips. The grain runs in gentle lines, dark and light, a pattern laid down by years of growth in some distant forest. The wood feels solid, continuous, unbroken. If you were to run your hand across it in the dim light of evening, you would feel its reality, its there-ness, its absolute presence in the world. This is the world we know. This is the world of objects and boundaries, of things that occupy space and resist our touch. A cup sits on the table. A book rests beside it. The air between them seems empty, but it too has substance, molecules of nitrogen and oxygen drifting in invisible currents, carrying the scent of old paper and perhaps a hint of rain from an open window somewhere nearby. For most of human history, this sensory world was thought to be the deepest truth. What you could see, what you could touch, what you could measure with your instruments, this was reality. The ancient Greeks imagined that if you took a piece of gold and cut it in half, then cut that half in half again, and continued this division, you would eventually arrive at a smallest piece, an atom, from the Greek word atomos, meaning indivisible. This smallest piece would be the final truth of matter, the irreducible kernel of goldness that could not be split further. But imagine now that we possess a knife sharper than any the Greeks could have dreamed of. Not a blade of bronze or iron, but the conceptual edge of human curiosity itself. We take our piece of gold, that soft yellow metal that has captivated humanity since the first nugget was pulled from a stream bed, and we begin to divide it. At first, the divisions are straightforward. A gram becomes a milligram becomes a microgram. We are still in the realm of the visible, or at least the measurable. Under a microscope, we can still see our golden fleck glinting in the light. But we continue. A microgram becomes a nanogram. We have entered a realm where the unaided human eye can no longer follow. We need instruments now, machines that can sense what our bodies cannot. And still we press deeper. We arrive at last at a single atom of gold, a structure so small that approximately 3,000 trillion atoms of gold would be needed to have the mass of a single gram. Try to imagine this number. It is a number so vast as to be almost meaningless to our everyday comprehension. And yet, this incomprehensibly tiny structure is what we once thought was the end of the journey. But it was not the end. It was barely the beginning. That single gold atom we discovered is not indivisible at all. It is a tiny solar system unto itself, with a dense nucleus at its center, and electrons occupying regions of space around it, though not in the neat circular orbits we once imagined. The nucleus itself, that dense core no more than 100,000th the diameter of the atom, is composed of protons and neutrons, bound together by forces that dwarf anything we experience in our everyday world. And those protons and neutrons? They too are composite structures, made of particles called quarks, held together by the exchange of particles called gluons, names that sound almost whimsical, but describe realities far stranger than their playful syllables suggest. We have descended, step by step, from the touchable world of wooden tables and golden rings into a realm where the very concepts of object and boundary begin to lose their meanings. This is the quantum realm, a domain of nature that operates according to rules so different from our everyday experience that even now, more than a century after its discovery, it retains an air of the impossible, the dreamlike, the unreal. But it is real, more real, in a sense, than the table beneath your hand, because everything you can touch, everything you can see, is built from these quantum foundations. The solidity of matter is an illusion created by countless quantum interactions happening faster than thought, more numerous than counting. Let us consider what it means to be small. In our everyday world, small is a relative term. A grain of sand is small compared to your hand. A bacterium is small compared to a grain of sand. But these are differences of degree, not of kind. A bacterium, for all its microscopic nature, still obeys the same basic rules as your hand. It occupies a definite position in space. It has a definite momentum, moving in a definite direction at a definite speed. If you knew enough about it, you could, in principle, predict its future trajectory with arbitrary precision. The quantum realm is not like this. The quantum realm is a place where smallness becomes a difference of kind, where the very nature of existence transforms into something our everyday intuitions cannot grasp. Consider an electron, one of the fundamental particles that orbit the nuclei of atoms. If you were to ask where this electron is located, you would be asking a question that has no definite answer. Not because we lack the instruments to measure it precisely, though that is also true, but because the electron itself does not have a definite position until the moment we look for it. This is not a poetic metaphor. This is not philosophical speculation. This is the observed, experimentally verified nature of reality at the quantum scale. Before we measure it, the electron exists in what we call a superposition of states. It is, in a sense that defies our classical logic, in many places at once. Not moving rapidly between these places, but genuinely, simultaneously present in a spread-out region of space. We describe this with a mathematical function called a wave function, a rippling entity that assigns probabilities to where the electron might be found if we were to look. Imagine a mist spread through a volume of space, thicker in some regions, thinner in others. Where the mist is thick, the electron is likely to be found. Where it is thin, the electron is unlikely to be found. But the electron is not a particle hiding somewhere within the mist. The electron is the mist, or rather, the mist describes all the possible ways the electron exists before we measure it. When we do measure the electron's position, when we send a photon to interact with it, or build a detector to sense its presence, something remarkable happens. The wave function, that spread-out mist of probability, collapses. The electron suddenly acquires a definite position. The many possibilities condense into a single actuality. This is called the collapse of the wave function, and it is one of the most profound and puzzling features of quantum mechanics. Why does observation cause this collapse? What counts as an observation? Is consciousness required, or is any physical interaction sufficient? These questions have haunted physicists and philosophers for nearly a century. They remain, in important ways, open questions, areas where the mathematics is clear, but the interpretation remains contested. But let us not lose ourselves yet in philosophy. Let us stay, for now, with the texture of this strange smallness. Let us feel our way through it like a hand extended in a darkened room, touching walls we cannot see, learning the shape of a reality that refuses to conform to our expectations. At the quantum scale, particles are not little billiard balls. They are not tiny planetary systems. They are entities that seem to have both wave-like and particle-like properties, though never both simultaneously in the same measurement. They are entities whose properties remain undefined until the moment we choose to measure them, as if reality itself is incomplete, perpetually unfinished, waiting for interaction to crystallize into definiteness. This might sound like science fiction, like a story told to entertain rather than inform. But every piece of modern electronics relies on these quantum principles. The computer or phone through which you might be listening to these words operates because engineers have learned to manipulate electron behavior at the quantum level. The LED lights that illuminate your room function because of quantum mechanics. The sun itself shines because of quantum tunneling, a phenomenon where particles pass through energy barriers they classically should not be able to cross. The quantum realm is not some distant abstraction. It is the foundation upon which all matter rests. Your body, every cell, every molecule, every atom, is a quantum system. The reason you do not notice quantum effects in your daily life is that they average out over the vast numbers of particles involved. When trillions upon trillions of atoms act together, their quantum uncertainties wash out, creating the illusion of classical, definite, predictable behavior. But peel back the layers, descend through the scales of size, and you find a world that operates by different rules. A world where position and momentum cannot both be known with perfect precision. A world where energy comes in discrete packets called quanta, not in continuous streams. A world where particles can exist in superpositions of states, being in multiple conditions simultaneously until measured. A world where separated particles can influence each other instantaneously across vast distances through a phenomenon called entanglement. This is the world we have discovered at the smallest scales of nature. And the remarkable thing, the truly humbling thing, is that we discovered it not through pure reasoning or philosophical meditation, but through careful experiment and observation. Nature herself revealed these truths to us, often against our will, often in ways that contradicted our deepest intuitions about how reality should behave. The story of quantum mechanics is a story of reluctant acceptance. Albert Einstein, one of its founders, spent much of his later life trying to prove that the theory was incomplete, that there must be hidden variables underneath the quantum randomness that would restore a deterministic, predictable universe. Niels Bohr, his friend and intellectual sparring partner, argued that no such hidden variables existed, that the probabilistic nature of quantum mechanics was fundamental and irreducible. The debates between these two giants of physics were profound and sometimes bitter. They were arguing not just about equations and experiments, but about the nature of reality itself. Is the universe deterministic or probabilistic? Are objects real when we're not looking at them? Does the moon exist when nobody is watching it? These were the questions that quantum mechanics forced scientists to confront. Questions that traditionally belonged to philosophers, but now demanded answers from physics. And slowly, through decades of experiments, nature provided her answer. The experiments favored Bohr. The universe, at its quantum foundations, appears to be fundamentally probabilistic. Hidden variables, if they exist, would have to have properties so strange, including instantaneous action at a distance, that they would be even more bizarre than accepting quantum mechanics at face value. So here we are, a century into the quantum age, still grappling with what it all means. We have learned to use quantum mechanics with extraordinary precision. We can predict the behavior of atoms and molecules, design new materials, build quantum computers that exploit superposition and entanglement to perform calculations impossible for classical machines. We can do all this while still not fully understanding what quantum mechanics tells us about the nature of reality. This is perhaps one of the most beautiful aspects of science. We can know that something is true, we can harness its power, and still we can wonder about its meaning. Quantum mechanics works. Every prediction it makes, when properly calculated, matches experimental results to astonishing precision. And yet it remains, in important ways, mysterious. As we continue this gentle exploration, we will delve deeper into specific aspects of quantum reality. We will explore the uncertainty principle, the strange duality of waves and particles, the spooky connections of entanglement. But all of these will be variations on the theme we have introduced here, the theme of a reality that refuses to be pinned down, that remains fluid and probabilistic, that challenges our very notion of what it means for something to exist. For now, as this first section comes to its quiet close, rest in this idea. Beneath the solid, predictable world of everyday experience lies a realm of profound strangeness, a realm where particles are also waves, where positions are probabilities, where the act of observation changes what is observed. This is not a defect in our knowledge. This is not a gap waiting to be filled by a better theory. This, as far as we can tell, is the way the universe actually is at its smallest scales. The quantum realm is the foundation of everything, and it is beautiful precisely because it is strange, precisely because it defies our expectations, precisely because it reminds us that reality is far richer, far more subtle, far more surprising than common sense would suggest. And now, having established our descent into smallness, let us turn to one of quantum mechanics' most famous principles, a principle that places fundamental limits on what we can know about this strange, small world. There is a certain comfort in knowing. When you place a book on a shelf, you know where it is. When you drive your car down a familiar road at a familiar speed, you know both where you are and how fast you're moving. These two pieces of information, position and velocity, seem like the most basic facts about any moving object. Together, they allow you to predict the future. If you know where something is and how fast it's going, you can calculate where it will be a moment from now, an hour from now, tomorrow. This ability to predict, this confidence in the knowability of the physical world, was the foundation of classical physics. Isaac Newton's mechanics, refined over centuries, rested on the assumption that if you knew the position and momentum of every particle in the universe at a single moment, you could, in principle, calculate the entire past and future of the cosmos. The universe, in this view, was like a vast clockwork mechanism, deterministic and predictable, its future already written in the precise positions and velocities of its particles. Pierre-Simon Laplace, the great French mathematician, expressed this most clearly when he wrote of an intelligence that could know all the forces of nature and the positions of all entities that compose it. Such an intelligence, he suggested, would find nothing uncertain. The future, like the past, would be present before its eyes. This was the dream of classical physics, perfect predictability through perfect knowledge. And then, in 1927, a young German physicist named Werner Heisenberg discovered something that shattered this dream at its quantum foundations. Heisenberg was working on the mathematics of quantum mechanics, trying to understand the behavior of electrons in atoms. He was dealing with matrices, arrays of numbers that described quantum states and their evolution. And in the course of his calculations, he discovered something remarkable and troubling. He found that there was a fundamental limit to how precisely you could know both the position and the momentum of a quantum particle simultaneously. The more precisely you measure one, the less precisely you can know the other. This was not a limitation of measurement technology. This was not something that could be overcome with better instruments or more careful technique. This was a fundamental feature of nature itself. The principle became known as Heisenberg's Uncertainty Principle, and it can be expressed with elegant simplicity. The uncertainty in position, multiplied by the uncertainty in momentum, must always be greater than or equal to a tiny number called Planck's constant divided by 4 pi. This number, Planck's constant, is extraordinarily small, approximately 6.6 times 10 to the negative 34 joule seconds. For everyday objects, this makes the uncertainty principle irrelevant. But for quantum particles like electrons, it becomes the dominant feature of their existence. Let us try to feel what this means. Imagine you wish to measure the position of an electron. To measure position, you must interact with the electron somehow. The most straightforward way is to shine light on it and observe the scattered photon. But here's the difficulty. To measure the position precisely, you need light with a very short wavelength, which means high energy. When this high energy photon strikes the electron, it gives the electron a kick, changing its momentum in an unpredictable way. You have succeeded in measuring the position precisely, but in doing so, you have disturbed the momentum. The more precisely you measure position, the more you disturb momentum. Conversely, if you use low-energy light to minimize the disturbance to momentum, the long wavelength means you cannot determine position precisely. This might sound like merely a measurement problem, a difficulty in observing without disturbing. And indeed, Heisenberg initially thought of it in these terms. But the deeper interpretation, the one that emerged as quantum mechanics matured, is more profound. The uncertainty is not just in our knowledge, it is in reality itself. Before measurement, the electron does not have a definite position and a definite momentum. It has a range of possible positions and a range of possible momenta, described by its wave function. The act of measurement causes the wave function to collapse into definite values. But the constraints imposed by the uncertainty principle mean that the wave function cannot be arbitrarily narrow in both position and momentum simultaneously. If the wave function is sharply peaked in position space, meaning the electron is confined to a small region, then it must be spread out in momentum space, meaning the electron's velocity is highly uncertain. If the wave function is sharply peaked in momentum space, meaning the electron has a well-defined velocity, then it must be spread out in position space, meaning the electron's location is highly uncertain. This is not a defect in quantum mechanics. This is not a gap waiting to be filled by a better theory. This is a fundamental feature of wave-like entities. And since quantum particles are described by wave functions, they inherit this unavoidable trade-off between position and momentum precision. The uncertainty principle applies to other pairs of quantities as well. Energy and time, for instance, are related by a similar uncertainty relation. The more precisely you know when an event occurs, the less precisely you can know the energy involved. The more precisely you determine the energy, the less precisely you can know the timing. This has profound implications. It means, for instance, that empty space is not truly empty. According to the uncertainty principle, there can be temporary violations of energy conservation as long as they happen quickly enough. Particle-antiparticle pairs can spontaneously appear out of the vacuum, exist for a fleeting moment, then annihilate back into nothingness. These are called virtual particles, and though they exist for times too short to directly observe, their effects are measurable. The Casimir effect is one such manifestation. If you place two uncharged metal plates very close together in a vacuum, they experience an attractive force. This force arises because the virtual particles that can exist between the plates are restricted to certain wavelengths by the boundaries, while outside the plates, virtual particles of all wavelengths can appear. This creates a pressure difference, pushing the plates together. The effect has been measured and verified, a tangible consequence of quantum uncertainty. The uncertainty principle also explains why atoms are stable. In classical physics, an electron orbiting a nucleus should radiate energy and spiral inward, causing the atom to collapse in a fraction of a second. But the uncertainty principle prevents this. If the electron were to fall into the nucleus, it would be confined to a very small region of space, which would imply a very large uncertainty in momentum, which would give it enormous kinetic energy. The lowest energy state, the ground state, is thus a compromise where the electron occupies a region around the nucleus, not at a precise distance, but spread out in a cloud of probability. Let us dwell for a moment on the philosophical implications of all this. In classical physics, uncertainty was merely practical. It reflected our ignorance, not any fundamental indeterminacy in nature. Given perfect information and perfect calculation, the future was in principle knowable. But quantum uncertainty is different. It is not ignorance. It is an irreducible feature of how the universe operates at small scales. This troubled many physicists, Einstein most famously among them. He could not accept that God, as he put it, played dice with the universe. He believed that quantum mechanics must be incomplete, that beneath the probabilities and uncertainties there must be hidden variables, unknown factors that would restore determinism if only we could access them. Einstein, along with Boris Podolsky and Nathan Rosen, published a paper in 1935 arguing that quantum mechanics could not be a complete description of physical reality. Their argument, now known as the EPR paradox, suggested that if quantum mechanics were complete, it would allow for what Einstein called spooky action at a distance, instantaneous influences between separated particles. Since such instantaneous actions seemed absurd, Einstein concluded that quantum mechanics must be missing something. Niels Bohr, the Danish physicist who was perhaps the deepest thinker about quantum mechanics' philosophical implications, responded to Einstein. Their debate, carried out through papers and letters and conversations over decades, was one of the great intellectual exchanges in the history of science. Bohr argued that quantum mechanics was complete, that the uncertainty and indeterminacy were fundamental features of nature, not gaps in our knowledge. For many years, this remained a philosophical debate. Both interpretations seemed viable. Experiments could not distinguish between a fundamentally probabilistic quantum mechanics and a deterministic, hidden variable theory that reproduced quantum predictions. But then, in 1964, a physicist named John Bell discovered something remarkable. Bell showed that any hidden variable theory that preserved locality, the principle that influences cannot travel faster than light, would make predictions that differ from quantum mechanics in certain carefully designed experiments. These predictions could be tested. Nature herself could arbitrate between Einstein's hidden variables and Bohr's quantum indeterminacy. The experiments were eventually performed, first by John Clauser and Stuart Friedman in the early 1970s, then by Alain Aspect in the early 1980s, then by many others with increasing sophistication. The results consistently favored quantum mechanics. Nature violated Bell's inequalities. The correlations between entangled particles were stronger than any local hidden variable theory could explain. This meant that either quantum mechanics' fundamental indeterminacy was real, or there were hidden variables, but they involved faster-than-light influences, or some other equally strange option held. Most physicists accepted the first option. The universe, at its quantum foundations, is genuinely probabilistic. The uncertainty is not in our knowledge, but in nature itself. And yet, and this is worth emphasizing, this probabilistic nature does not mean anything goes. Quantum mechanics makes extraordinarily precise predictions about probabilities. If you perform an experiment 1,000,000 times, quantum mechanics will tell you with stunning accuracy how many times you will get each possible result. What it cannot tell you is which result you will get on any particular trial. It is like knowing the exact odds in a fair die roll, 1/6 for each face, but never being able to predict which face will appear on the next throw. The statistics are deterministic, the individual outcomes are not. This is the nature of quantum reality as revealed by the uncertainty principle. There is something almost poetic about this. The universe at its foundations is not clockwork. It is not rigid and predetermined. There is a kind of looseness, a play in the joints of reality. The future is not written in the present. There are genuine alternatives, genuine possibilities, and nature chooses between them probabilistically according to precise rules, but without any underlying reason for each individual choice. Some find this disturbing. The loss of determinism feels like a loss of comprehensibility. If we cannot, in principle, predict individual quantum events, if we can only predict their statistical distributions, then it seems as though something essential has been removed from our understanding of nature. We are left with probabilities instead of certainties, clouds instead of particles, waves instead of trajectories. But others find it liberating. A deterministic universe is a universe where everything is already decided, where the present state contains the entire future encoded within it, like a seed contains the full-grown tree. A probabilistic universe is one where the future genuinely remains open, where new information comes into being with each quantum event, where creation is ongoing and perpetual, rather than merely the unfolding of initial conditions. Neither view can be proven philosophically. Both are compatible with the mathematics of quantum mechanics. What we do know with experimental certainty is that Heisenberg's uncertainty principle holds. Position and momentum cannot both be determined with arbitrary precision. Energy and time are similarly constrained. The quantum world is irreducibly fuzzy, not because of our limitations, but because fuzziness is woven into the fabric of reality at small scales. And perhaps there is something appropriate about this, something fitting. For a universe to contain consciousness, for matter to organize itself into structures capable of wondering about their own existence, perhaps some looseness at the foundations is necessary. Perfect determinism might be too rigid to permit the kind of complex, adaptive, creative processes that gave rise to life and mind. This is speculation, of course. We do not know why the universe has the quantum properties it does. We do not know why uncertainty is fundamental rather than merely practical. These are questions at the boundary between physics and philosophy, where equations give way to interpretation, where experiment gives way to meaning. What we do know is this: the dance of uncertainty is not a defect, but a feature. It is not something to be eliminated, but something to be understood, and perhaps, in time, appreciated. The quantum world does not grant us the absolute knowledge that classical physics promised, but it gives us something else, a reality that is richer, stranger, more subtle than the clockwork cosmos of Newton and Laplace. As we move forward in our exploration, we will see how this uncertainty interweaves with other quantum phenomena. We will see how particles that are also waves navigate this uncertain terrain. We will see how measurement and observation fit into this picture. We will see how entanglement connects distant particles in ways that respect the uncertainty principle, while still allowing for correlations that Einstein found spooky. But for now, rest in this central idea. At the quantum scale, there are limits to what can be known. Not limits of technology or technique, but limits built into the structure of nature itself. Position and momentum, energy and time exist in a kind of complementarity, where precision in one necessarily brings imprecision in the other. This is the dance of uncertainty, and every quantum particle performs it, every moment, in the depths of atoms and in the spaces between. It is a dance without choreography, guided by probability rather than script, creating the present moment by moment, rather than following a predetermined path laid down at the universe's beginning. And now, with this understanding of uncertainty in place, let us turn to another of quantum mechanics' deep mysteries, the strange dual nature of light and matter, neither fully wave nor fully particle, but something that transcends both categories. Picture a pebble thrown into a still pond on a quiet morning. The pebble breaks the surface and sinks, but it leaves something behind, ripples spreading outward in perfect circles, wave after wave, carrying the disturbance across the water. These are waves, and we know what waves are. They are patterns of disturbance that propagate through a medium. Water waves need water. Sound waves need air or another material to travel through. Waves spread out, interfere with each other, diffract around obstacles. They are extended in space, continuous, flowing. Now picture instead a grain of sand, a single tiny particle of silicon dioxide, complete and discrete. It occupies a definite position in space. If you know its location and velocity, you can predict where it will be a moment later. It does not spread out or diffract. It is here or there, never both. never smeared across space in a wave-like manner. This is a particle, localized and definite. For centuries, natural philosophers debated whether light was a wave or a particle. Isaac Newton believed light consisted of tiny particles, which he called corpuscles, streaming from luminous objects. This explained why light traveled in straight lines and cast sharp shadows. Christian Huygens, Newton's contemporary, argued that light was a wave because this better explained phenomena like reflection and refraction. The wave theory eventually won out in the 19th century, when experiments by Thomas Young and others demonstrated interference and diffraction of light, phenomena that seemed impossible to explain with particles, but natural for waves. Young's double-slit experiment was particularly convincing. When light passes through two closely spaced slits, it creates an interference pattern on a screen, alternating bands of light and darkness that can only be explained if light waves from the two slits add together and cancel each other out in different regions. And then, just when it seemed settled that light was definitively a wave, requiring a medium called the luminiferous ether to propagate through, Max Planck discovered something puzzling. In 1900, while studying the spectrum of light emitted by hot objects, he found that he could only explain the observations if he assumed that light energy came in discrete packets, or quanta, rather than in continuous waves. The energy of each quantum was proportional to the frequency of the light, with Planck's constant as the proportionality factor. Albert Einstein extended this idea in 1905, proposing that light itself consisted of these quanta, later called photons. He used this to explain the photoelectric effect, where light striking a metal surface can eject electrons. The key observation was that the energy of the ejected electrons depended on the frequency of the light, not its intensity. Bright red light could not eject electrons, no matter how intense it was, while dim ultraviolet light could, because each ultraviolet photon carried more energy than each red photon. This was deeply perplexing. Light behaved as a wave in some experiments and as particles in others. It was as if nature refused to commit to a single identity, showing different faces depending on how you looked. Interference and diffraction said wave. The photoelectric effect said particle. Both aspects were real. Both were experimentally verified. And yet they seemed fundamentally incompatible. Then, in 1924, a young French physicist named Louis de Broglie proposed something even more radical. If light waves could behave like particles, he reasoned, perhaps particles could behave like waves. Perhaps matter itself, electrons and atoms and everything else, had a wave-like aspect. De Broglie suggested that every particle had an associated wavelength, inversely proportional to its momentum. For everyday objects like baseballs and people, this wavelength would be inconceivably small, far too tiny to detect. But for tiny particles like electrons, the wavelength could be large enough to produce observable wave-like effects. This was received with skepticism. Matter as waves seemed too strange, too divorced from common sense. But then, just 3 years later, Clinton Davison and Lester Germer performed an experiment that confirmed de Broglie's hypothesis. They scattered electrons off a crystal of nickel and observed a diffraction pattern, just as one would expect from waves passing through a regular array of obstacles. Electrons, those tiny particles of matter, those units of negative charge that orbit atomic nuclei, were also waves. The wave-particle duality was not unique to light. It was a universal feature of nature at the quantum scale. Everything, photons, electrons, atoms, even molecules, exhibited both wave and particle properties. But what does it really mean to be both wave and particle? This is where quantum mechanics becomes not just mathematically challenging, but conceptually demanding. Classical categories of wave and particle are inadequate. Quantum entities are neither waves nor particles in the classical sense. They are something else, something for which we do not have a perfect everyday analogy, but which manifests as wave-like in some experimental contexts and particle-like in others. The two-slit experiment, which Thomas Young used in the early 1800s to demonstrate light's wave nature, becomes even more profound when performed with particles that have mass, like electrons. Let us walk through this experiment slowly, feeling our way through its implications. Imagine a barrier with two narrow slits cut into it. Behind the barrier is a detection screen that lights up wherever a particle hits it. We send electrons, one at a time, toward the barrier. Each electron is a discrete entity with charge and mass. When it hits the detection screen, it makes a single, tiny flash at a single location. If we cover one slit and send electrons through the other, we see a simple pattern on the screen. A bright band directly behind the open slit, gradually fading as we move away from it. This is what we expect from particles. Now we cover the second slit and open the first, and again we see a single bright band centered behind the newly opened slit. Here is where it gets strange. When we open both slits and send electrons through, we do not see the sum of the two single-slit patterns. Instead, we see an interference pattern, multiple bands of light and darkness on the screen, just like the pattern produced by waves. The electrons, somehow, are interfering with themselves, as if each electron is a wave that passes through both slits simultaneously and interferes with itself on the way to the screen. But each electron arrives at the screen as a particle, making a single flash at a single location. If we send electrons one at a time, with long intervals between them, the interference pattern builds up gradually, flash by flash. Each electron seems to pass through both slits, but each electron hits the screen at only one location. Over time, the individual hits accumulate into an interference pattern. This is profoundly strange. If the electron goes through the left slit, how does it know about the right slit? If it goes through both slits, why does it arrive at the screen as a localized particle rather than as a spread-out wave? And most puzzling of all, if we try to determine which slit the electron actually went through by placing a detector at one or both slits, the interference pattern disappears. The mere act of determining the electron's path causes it to behave like a classical particle, and the wave-like interference vanishes. This is called the observer effect, though that name is somewhat misleading. It is not that a conscious observer is required, rather any interaction that provides which path information. Any physical process that couples the electron to a detecting system in a way that records which slit it passed through causes the wave function to decohere, to lose its coherent superposition of passing through both slits. The mathematics describes this beautifully with wave functions and superposition. When both slits are open and we do not measure which path the electron takes, its wave function is a superposition of two components, one corresponding to passing through the left slit, one corresponding to passing through the right slit. These two components are waves that can interfere with each other, and the interference shows up in the probability distribution of where the electron might be detected on the screen. When we measure which slit the electron passes through, we collapse the wave function. The superposition is destroyed. The electron is now definitely in one path or the other, no longer in both simultaneously, and without superposition, there can be no interference. The wave-like behavior disappears, leaving only particle-like behavior. This is complementarity, a concept introduced by Niels Bohr. Wave and particle are complementary aspects of quantum reality. They cannot both be fully manifested in the same experimental setup. Experiments that reveal wave properties necessarily obscure particle properties, and vice versa. Which aspect you see depends on what questions you ask. what measurements you perform. Some have interpreted this to mean that observation creates reality, that consciousness somehow collapses the wave function and brings definite properties into existence. This is a dramatic interpretation, favored by some philosophers, but viewed with skepticism by most physicists. The more conservative interpretation is that measurement, as a physical interaction, entangles the quantum system with the measuring apparatus, and this entanglement is what causes decoherence and the appearance of wave function collapse. But regardless of interpretation, the empirical fact remains. Quantum entities exhibit wave-particle duality. They are neither pure waves nor pure particles. They are quantum objects whose behavior depends on the experimental context. In some contexts, their wave nature dominates. In other contexts, their particle nature dominates. But they are always, fundamentally, quantum entities that transcend the classical categories. This duality extends beyond electrons and photons. Atoms have been shown to interfere with themselves. Molecules composed of dozens of atoms have produced interference patterns. There are experiments where even larger structures, approaching the boundary between quantum and classical, show wave-like behavior. The duality is not limited to special quantum particles. It is a universal feature of matter and energy, and yet we do not see this duality in everyday life. Baseballs do not interfere with themselves. People do not exist in superpositions of being in multiple places at once. Why not? The answer lies in a process called decoherence, mentioned earlier but worth exploring more fully. Decoherence occurs when a quantum system interacts with its environment. A baseball traveling through air is constantly colliding with air molecules, photons from light sources, cosmic rays, and countless other particles. Each of these interactions is essentially a measurement, providing information about the baseball's trajectory. These constant measurements destroy any quantum superposition almost instantaneously, leaving only classical behavior. For an electron in a carefully isolated system, or a single photon in a vacuum, interactions with the environment can be minimized. Superpositions can persist long enough for wave-like behavior to be observed. But for macroscopic objects, decoherence is essentially instantaneous. The quantum nature is still there in principle, but it is washed out by the overwhelming flood of environmental interactions. So the classical world emerges from the quantum world through decoherence. The appearance of definite positions and trajectories is not because large objects somehow transcend quantum mechanics, but because their quantum superpositions are constantly being destroyed by interactions with the environment. The wave-particle duality is still there, technically, but it is hidden beneath layers of decoherence. There is something almost melancholic about this. At the smallest scales, reality retains a kind of fluidity, an openness, a multiplicity of possibilities. But as systems grow larger and more interconnected with their surroundings, this quantum richness fades. The sharp, definite, classical world emerges, beautiful and functional, but somehow less mysterious, less full of potential. And yet, even in the classical world, we are reminded that quantum mechanics is the foundation. Every time you see a color, you are witnessing quantum transitions in atoms. Every time you feel the solidity of matter, you are feeling quantum repulsion between electron clouds. Every star that shines does so because of quantum tunneling in nuclear fusion. The quantum substrate is always there, even when its more exotic effects are hidden. Let us consider one more aspect of wave-particle duality before we move on: the concept of the wave function itself. In quantum mechanics, every particle is described by a wave function, typically denoted by the Greek letter psi. This wave function is not a physical wave in ordinary space. It is a mathematical function that encodes the probabilities of finding the particle in various states. When you measure a particle's position, The absolute square of the wave function at each location gives the probability of finding the particle there. The wave function itself can be complex valued, involving imaginary numbers, and it evolves according to the Schrödinger equation, a wave equation that describes how quantum states change over time. The wave function is central to quantum mechanics, yet its ontological status, what it actually is in reality, remains debated. Is it a real physical entity, a field that exists in space and somehow guides particle behavior? Or is it merely a mathematical tool, a way of encoding our knowledge about probabilities without corresponding to anything physical? Different interpretations of quantum mechanics answer these questions differently. In the Copenhagen interpretation, the wave function is not directly real, but represents the potential for various outcomes. Upon measurement, it collapses from a superposition of possibilities into a single actuality. In the many worlds interpretation, the wave function never collapses. Instead, all possibilities are realized in different branches of a constantly splitting universe, and what we perceive as collapse is merely our subjective experience of following one particular branch. In pilot wave theories, particles have definite positions all along, guided by a real physical wave described by the wave function. These interpretational debates show how deep the mystery of wave-particle duality runs. It is not merely a technical puzzle solved by the mathematics of quantum mechanics. It is a conceptual challenge that forces us to question our fundamental categories for understanding nature. What is a particle? What is a wave? What does it mean to exist? These questions, raised by wave-particle duality, touch on the deepest issues in philosophy of science and metaphysics. And perhaps that is fitting. Science, at its best, does not just provide answers. It also reveals deeper questions, layers of mystery beneath the surface of everyday experience. Wave-particle duality does both. It answers the question of how light and matter behave at small scales, providing precise mathematical predictions confirmed by countless experiments. But it also raises profound questions about the nature of reality that remain, in important ways, open. As we bring this section to a close, let us hold this central insight. The quantum world does not divide neatly into waves and particles. These are classical concepts, useful but ultimately inadequate. Quantum entities are something else, something that can manifest wave-like properties in some contexts and particle-like properties in others, but that exists in a realm beyond these classical categories. The electron is not a tiny billiard ball, nor is it a ripple in some medium. The photon is not a pure particle of light, nor is it a pure wave in the electromagnetic field. They are quantum objects, entities whose full nature transcends our everyday intuitions, but whose behavior can be precisely described by the mathematics of quantum mechanics. And now, having explored the strange duality of waves and particles, having seen how quantum entities refuse to fit into classical categories, let us turn to perhaps the most perplexing phenomenon in all of quantum mechanics: entanglement, the strange connection that can exist between separated particles, linking them in ways that Einstein called spooky. Imagine two dancers, trained together for years, who know each other's movements so intimately that even when separated, even when moved to opposite ends of a vast stage, they remain somehow coordinated. When one turns left, the other turns right, maintaining perfect symmetry without seeing each other, without any signal passing between them. This is a pale metaphor, an imperfect analogy, but it gestures towards something real in quantum mechanics: entanglement. Entanglement occurs when two or more quantum particles interact in such a way that their quantum states become correlated. After the interaction, even when the particles are separated by large distances, measuring the state of one particle instantaneously determines the state of the other, not influences precisely, but reveals, though the distinction between these becomes philosophically subtle. The phenomenon was first clearly articulated in the EPR paper we mentioned earlier, where Einstein, Podolsky, and Rosen used it to argue that quantum mechanics must be incomplete. They imagined a scenario where two particles are prepared in an entangled state such that their properties are perfectly correlated. For instance, their spins might be opposite. If one particle spins up when measured, the other must spin down. According to quantum mechanics, before measurement, neither particle has a definite spin. Both exist in superpositions of spin up and spin down. But once you measure one particle and find its spin up, the other particle's wave function instantaneously collapses to spin down, no matter how far away it is. Einstein found this absurd. How could measuring one particle here instantaneously affect another particle there, potentially light years away? He called it spooky action at a distance, and he argued that the only reasonable explanation was that the particles must have had definite properties all along, hidden from us until measurement, but real nonetheless. In other words, there must be hidden variables that quantum mechanics does not describe, and these hidden variables carry the information that makes the correlations possible without any instantaneous influence. This seemed like a sensible position. After all, if you prepare two coins such that one is heads and the other is tails, then separate them and later look at one to find heads, you immediately know the other is tails. But this knowledge does not involve any spooky action. The coins had their values all along. You simply learned what was already the case. The question was whether quantum entanglement could be understood this way, as correlations established at the moment of interaction and simply revealed later by measurement, or whether something stranger was happening. For decades, this remained a philosophical question, without any way to experimentally distinguish between these views. Then, in 1964, John Bell discovered a way to test whether hidden variables could explain quantum correlations. His insight was to consider measurements along different axes. For spin, you can measure along any direction, vertical, horizontal, or any angle in between. Bell showed that if correlations were due to hidden variables, established at the moment of entanglement, then measurements along different axes would satisfy certain inequalities, now called Bell inequalities. Quantum mechanics, on the other hand, predicted violations of these inequalities. The correlations it predicted were stronger than any hidden variable theory respecting locality, the principle that influences cannot travel faster than light could produce. So here, finally, was a testable distinction between hidden variables and quantum mechanics. The experiments were performed, first in the 1970s and 80s, then with increasing sophistication into the present day. The results consistently violated Bell's inequalities. The correlations between entangled particles were stronger than local hidden variables could explain. Nature sided with quantum mechanics, or at least with some theory involving non-locality or another exotic feature. So what does this mean? If hidden variables are ruled out, or at least local hidden variables, then what is happening? One interpretation is that measurement on one particle really does instantaneously affect the other particle, but in a way that cannot be used to transmit information faster than light. The collapse of the wave function, if we take it literally, is a non-local process. Another interpretation, more common among physicists today, is that entanglement reveals the non-separability of quantum systems. When two particles become entangled, they are no longer independent entities with separate states. Instead, they form a single quantum system described by a joint wave function. The system has definite properties, but the individual particles do not, until measurement forces the system to split into definite outcomes for each particle. In this view, entanglement is not so much about influence as about wholeness. The entangled particles are not two separate things coordinating their behavior. They are one quantum system whose parts remain connected in a way that transcends spatial separation. Measurement reveals correlations that were always there, not as hidden properties of the individual particles, but as properties of the entangled whole. Let us try to feel this through a specific example. Consider a photon, a particle of light that spontaneously splits into two lower energy photons through a process called spontaneous parametric downconversion. Conservation laws ensure that certain properties are shared between the two daughter photons. Their polarizations, for instance, might be correlated such that if one is horizontally polarized, the other is vertically polarized. Before measurement, quantum mechanics describes each photon as being in a superposition of horizontal and vertical polarization. Not sometimes horizontal and sometimes vertical, but genuinely both until measured. The two-photon system is in an entangled state where the polarizations are opposite but undefined. Now send these photons in opposite directions, one to the left and one to the right, until they are separated by many meters or kilometers, or in principle, even light years. Place polarization detectors at both ends. When you measure the left photon and find it horizontally polarized, the right photon's state instantaneously becomes vertically polarized. But, and this is crucial, you cannot use this to send a message. The person on the right, looking at their photon, sees a random sequence of horizontal and vertical polarizations. They see nothing to suggest that their results are correlated with measurements happening far away on the left. Only when both parties compare their results do they discover the perfect anti-correlation. So, quantum entanglement does not violate the relativistic prohibition on faster-than-light signaling, even though it involves correlations that are, in some sense, instantaneous. This is one of the subtle features that makes quantum mechanics compatible with special relativity, despite the initial appearance of conflict. Entanglement is not just a theoretical curiosity. It is now a practical resource used in emerging quantum technologies. Quantum cryptography, for instance, relies on entanglement to create secure communication channels. Because any eavesdropper trying to measure the entangled particles would disturb their quantum state, their presence would be immediately detectable, making the code theoretically unbreakable. Quantum computers also rely on entanglement. Classical computers process information using bits that are either 0 or 1. Quantum computers use qubits that can be in superpositions of 0 and 1. When multiple qubits become entangled, the quantum computer can explore many computational paths simultaneously, offering exponential speed-up certain types of problems. The challenge in building quantum computers is maintaining entanglement long enough for computations to complete. Decoherence, the process we discussed earlier where quantum superpositions are destroyed by interactions with the environment, constantly threatens to collapse the carefully prepared entangled states. Quantum error correction, which uses redundancy to protect quantum information, is one approach to this problem, though it requires far more qubits than are currently available. But beyond these practical applications, entanglement remains deeply puzzling from a conceptual standpoint. It challenges our intuition about separability, the notion that distant objects are independent of each other. In the quantum world, two particles can become so intimately connected that they must be treated as a single entity, even when separated by vast distances. This has led some physicists and philosophers to suggest that space itself might be emergent from entanglement. Perhaps at the deepest level, the universe is not a collection of separate things located in space, but rather a vast network of quantum correlations, and what we perceive as space is a higher-level description of the patterns in this network. This is speculative, and it ventures into the territory where quantum mechanics meets quantum gravity, a synthesis that remains incomplete. But it shows how entanglement, this strange correlation between separated particles, might be pointing toward deep truths about the nature of space, time, and reality itself. There are different types of entanglement worth noting. What we have discussed so far involves pairs of particles, but larger groups can become entangled in even more complex ways. Multi-particle entanglement creates states that cannot be understood as collections of pairwise entanglements. These states have their own unique properties and potential applications. There is also the distinction between pure entanglement and mixed states. Pure entanglement occurs when particles are in a definite quantum superposition with no randomness beyond quantum uncertainty. Mixed states involve classical randomness as well, where you have statistical uncertainty about which quantum state the system is in. Mixed states can still exhibit correlations, but they lack some of the stronger features of pure entanglement. Measuring the degree of entanglement is itself a subtle problem. For 2 qubits, there are well-defined measures like concurrence or entanglement entropy, but for larger systems, quantifying entanglement becomes more difficult, and there are different measures that capture different aspects of quantum correlation. Entanglement also plays a role in the measurement problem, that deep puzzle about what happens when we observe a quantum system. In the Copenhagen interpretation, measurement causes wave function collapse. But if we treat the measuring apparatus quantum mechanically, it becomes entangled with the system being measured rather than collapsing its wave function. This leads to what Schrödinger called the problem of macroscopic superpositions. If a quantum particle in a superposition of 2 states becomes entangled with a measuring device, and we treat the whole system quantum mechanically, then the device itself enters a superposition of having measured 2 different outcomes. And if a person reads the device, that person becomes entangled, entering a superposition of having seen 2 different results. Where does this chain stop? When does superposition give way to definite outcomes? The Copenhagen interpretation says that measurement causes collapse, but this seems to require drawing an arbitrary line between quantum and classical systems. The many worlds interpretation says the chain never stops, that all branches continue to exist, and we simply find ourselves in one branch without being aware of the others. Decoherence provides a partial answer, showing how entanglement with the environment creates the appearance of collapse without requiring any fundamental divide between quantum and classical. These questions remain open, debated, explored. Entanglement sits at the heart of many of them because it reveals how quantum correlations can link separated systems in ways that resist any simple separability. It forces us to think of the universe not as a collection of independent parts, but as an interconnected whole, where the properties of one part can be indefinable until related to another part, even when the parts are far apart. There is something almost beautiful about this, something that resonates with ancient holistic philosophies, while remaining firmly grounded in mathematical precision and experimental verification. The universe, at its quantum foundations, is not atomistic in the classical sense. It is a web of relationships, correlations, connections that transcend spatial separation. And yet, this beauty is strange, challenging, difficult to accept. It violates our deeply rooted intuition that objects have their properties independently of observation, that space separates things into truly distinct entities, that information cannot be correlated faster than light allows. Entanglement respects the letter of relativity, no signals faster than light, but it seems to violate its spirit, creating correlations that appear instantaneous. Einstein was right to be troubled by this. It is troubling. It suggests that our ordinary concepts of objects, space, and independence are approximations that work well in everyday life, but fail at the quantum level. The world is not made of separate things that happen to interact. It is made of interactions, correlations, relationships, and the apparent separateness of things emerges from these relationships rather than being fundamental. This is one of quantum mechanics' deepest lessons, delivered through the phenomenon of entanglement. And like so much in quantum mechanics, it is a lesson we can accept mathematically, use practically, and yet still struggle to fully comprehend. The equations are clear, the experiments are decisive, but the meaning, the interpretation, the philosophical implications, these remain subjects of ongoing exploration and debate. As we prepare to move beyond entanglement toward our final section, reflecting on the broader philosophical implications of quantum mechanics, let us hold in mind this image: two particles, separated by any distance, sharing a single quantum state. Neither particle has definite properties on its own. Together, they form a whole that transcends their spatial separation. Measure one, and you immediately know something about the other, not because a signal passed between them, but because they were never truly separate to begin with. This is entanglement, the strange intimacy at the heart of quantum reality, connecting what classical physics would keep forever apart, revealing a universe more interconnected, more holistic, and more mysterious than our everyday experience suggests. And now, with these technical aspects of quantum mechanics in place, the uncertainty, the wave-particle duality, the entanglement, let us turn to the broader philosophical whisper that emerges from these phenomena, asking what quantum mechanics might teach us about the nature of reality, knowledge, and existence itself. We have journeyed deep into the quantum realm, descending from the familiar world of solid objects and definite properties into a domain where particles are also waves, where measurement creates reality, where separated things remain mysteriously connected. Now, as our exploration draws toward its quiet close, let us step back and ask what all of this means. What does quantum mechanics teach us about the nature of reality itself? This is not a question that physics alone can answer. The mathematics of quantum mechanics is precise and extraordinarily successful at predicting experimental results. But mathematics describes how things behave, not what they fundamentally are. To move from behavior to being, from prediction to interpretation, we must venture into philosophy, where different answers remain possible and debates continue. Perhaps the most conservative position is instrumentalism, the view that scientific theories should not be taken as descriptions of reality, but merely as tools for predicting observations. From this perspective, quantum mechanics is simply a computational algorithm. You input information about initial conditions and measurements you plan to perform, and it outputs probability distributions for possible outcomes. Whether wave functions are real, whether particles have properties before measurement, whether superpositions genuinely exist, these questions are meaningless from the instrumentalist perspective because they ask about things beyond the realm of prediction and observation. Many physicists adopt something like this stance in their daily work, not because they have carefully considered the philosophy, but because focusing on predictions and experiments, rather than metaphysical questions, is practically useful. Physics proceeds by calculation and verification, and instrumentalism justifies setting aside deeper questions in favor of getting work done. But instrumentalism feels incomplete to many, perhaps even evasive. Science seems to reveal truths about nature, not just patterns in our observations. When we discover that matter is made of atoms, we do not merely mean that atomic theory makes good predictions. We mean that atoms actually exist. Similarly, when quantum mechanics tells us about wave functions and superpositions, it seems to be telling us something about how nature actually is, not just how our measurements will turn out. This leads to realist interpretations, which take quantum mechanics to describe genuine features of reality. But here the paths diverge, because different realist interpretations answer the key questions differently. What happens during measurement? Do superpositions really exist? Is reality deterministic or probabilistic? Different interpretations give different answers while agreeing on predictions. The Copenhagen interpretation, dominant for much of the 20th century, was developed primarily by Niels Bohr and Werner Heisenberg. In this view, the wave function describes the potential for various measurement outcomes, but not a definite reality before measurement. Measurement causes wave function collapse, turning potential into actuality. Before you measure an electron's position, it does not have a definite position. The act of measurement brings definite position into being. This interpretation embraces complementarity, the idea that wave and particle are complementary aspects revealed by different experimental contexts, and neither is the complete truth. It also embraces the centrality of measurement, suggesting that quantum mechanics is fundamentally about the interface between the quantum system and the classical measuring apparatus. Critics point out that the Copenhagen interpretation leaves much undefined. What counts as a measurement? When exactly does the wave function collapse? Where is the boundary between quantum and classical? If measurement is a physical process, why should it have this special status of causing collapse? These questions do not have clear answers within the Copenhagen framework, leading some to seek alternatives. One such alternative is the many worlds interpretation, proposed by Hugh Everett in 1957. This interpretation takes the wave function as completely real and denies that collapse ever happens. Instead, when a measurement occurs, the wave function branches. All possible outcomes are realized, but in different branches that no longer interact with each other. You experience one particular outcome because your consciousness exists in one particular branch, but other versions of you experience other outcomes in other branches. In this view, the Schrödinger equation, the fundamental equation governing quantum evolution, is never violated. The apparent collapse is simply the subjective experience of finding yourself in one branch of a constantly branching reality. The cat in Schrödinger's thought experiment is not in a superposition of alive and dead, nor does measurement cause collapse to one state or the other. Instead, the universe branches into two versions, one where the cat is alive and one where it is dead. And there are two versions of you, one in each branch, observing one outcome or the other. Many worlds solve some problems. No need for wave function collapse, no special role for measurement, no quantum classical boundary, but creates others. If all outcomes happen in different branches, how should we understand probability? Why do we experience some outcomes more often than others in our branch? And perhaps most troubling, the proliferation of branches seems extravagant, multiplying reality beyond necessity. Every quantum event anywhere in the universe causes branching, creating countless new branches every moment. Yet many worlds has gained adherence, particularly among physicists working on quantum gravity and cosmology, because it treats the wave function as fundamentally real and allows the Schrödinger equation to hold universally without exceptions. It is an elegant interpretation in some respects, though it asks us to believe in an enormous, perhaps infinite, number of parallel realities. Another interpretation, pilot wave theory or Bohmian mechanics, takes a different approach. It says that particles always have definite positions, guided by a real quantum wave that evolves according to the Schrödinger equation. The wave is not just a mathematical tool for calculating probabilities. It is a physical field that guides particle motion. Measurement reveals the positions that were there all along, and the apparent randomness in quantum mechanics comes from our ignorance of the exact initial positions, which we cannot know due to the practical limitations of measurement. Pilot wave theory restores determinism and definiteness to quantum mechanics. Particles have trajectories. The uncertainty principle reflects epistemological limitations, not ontological indeterminacy. But the price is non-locality. The quantum wave guiding one particle can depend instantaneously on the positions of distant particles, creating the spooky action at a distance that Einstein found objectionable. Pilot wave theory preserves realism, but abandons locality. These are just three major interpretations among many. There are also objective collapse theories, which modify the Schrödinger equation to include spontaneous collapse events that become more frequent as systems grow larger, explaining the emergence of classicality without requiring measurement. There are relational interpretations, which say that quantum states are always defined relative to other systems, not absolutely. There are consistent histories approaches, which focus on sets of histories that are consistent with quantum laws, rather than trying to describe what happens at each moment. The proliferation of interpretations reveals something important. The empirical success of quantum mechanics does not uniquely determine its metaphysical implications. Multiple stories about what is really happening can give rise to the same predictions, and experiments cannot distinguish between them if the predictions are identical. This is sometimes called the underdetermination of theory by evidence, and it is a general feature of science, not unique to quantum mechanics, but particularly stark here. What should we make of this? One response is to embrace pluralism, accepting that there may be multiple valid ways of thinking about quantum reality, each illuminating different aspects without any being uniquely correct. Another response is to wait for new experiments or theoretical developments that might distinguish between interpretations. A third response is to focus on extensions of quantum mechanics, like quantum field theory and quantum gravity, hoping that deeper theories will clarify interpretational questions. Quantum field theory, which combines quantum mechanics with special relativity, treats particles not as fundamental entities, but as excitations in underlying fields that permeate all of space. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. This shifts the ontology from particles to fields, and some of the interpretational puzzles change form in this context, though they do not disappear entirely. Quantum gravity, which aims to unite quantum mechanics with general relativity, remains incomplete. String theory, loop quantum gravity, and other approaches offer partial pictures, but no consensus has emerged. One hope is that a successful theory of quantum gravity will clarify what quantum mechanics means, perhaps by showing that space and time themselves are emergent from something more fundamental, or by revealing new principles that constrain interpretation. But perhaps the interpretational questions will persist even with deeper theories. Perhaps there is an irreducible aspect of reality that remains beyond the reach of physics, not because of practical limitations, but because certain metaphysical questions do not have empirical answers. This would not make them unimportant. Understanding the nature of reality, even if that understanding cannot be settled by experiment alone, remains a worthwhile philosophical endeavor. Beyond interpretation, quantum mechanics raises questions about the nature of knowledge. The uncertainty principle tells us there are fundamental limits to what can be known. Not limits of our current technology or our current theories, but limits built into the fabric of nature. Position and momentum, energy and time cannot both be known with arbitrary precision. Is this a limit on knowability in principle, or does it mean that the properties simply do not have definite values until measured? Different interpretations answer differently. Copenhagen says the properties are indefinite until measurement, so the uncertainty reflects a genuine incompleteness of reality before measurement. Pilot wave theory says the properties are definite but unknowable, so the uncertainty reflects epistemological limitations. Many worlds says the properties have all possible values across different branches, so the uncertainty reflects your subjective experience of being in one branch rather than another. The common thread is that quantum mechanics undermines a certain kind of epistemic optimism that characterized classical physics. In the classical worldview, perfect knowledge was possible in principle, even if unattainable in practice. Know the positions and momenta of all particles at one moment, and the future was determined. Quantum mechanics denies this. Even perfect knowledge of a quantum state does not determine future measurement outcomes with certainty, only probabilities. This has implications for concepts like determinism and free will. If the universe is fundamentally probabilistic at the quantum level, then it is not deterministic. The future is genuinely open in a way it would not be in a classical universe. Does this provide room for free will? Perhaps, though the connection is not straightforward. Quantum randomness is still randomness, not agency. An unpredictable universe is not the same as a universe with free will, which presumably requires not just indeterminism, but some kind of control or intentionality. Still, quantum mechanics removes one argument against free will, the argument that physical determinism leaves no room for genuine choice. If physical processes are not deterministic, then the kind of free will that requires alternate possibilities might be compatible with physics after all. This does not prove free will exists, but it removes one obstacle to believing in it. Quantum mechanics also raises questions about consciousness and observation. The role of measurement in quantum mechanics, particularly in the Copenhagen interpretation, seems to give observers a special status. This has led some to suggest that consciousness is required for wave function collapse, that minds interact with quantum reality in a unique way. Most physicists are skeptical of this. Measurements can be performed by unconscious apparatus, and decoherence explains the appearance of collapse without invoking consciousness. But the questions persist. Is consciousness itself a quantum phenomenon? Do quantum effects in the brain play a role in cognition? These are areas of ongoing research, particularly in the field of quantum biology, but so far the evidence suggests that biological systems rely primarily on classical physics, with quantum effects playing only minor roles. Yet the questions remain intriguing. Some researchers have proposed that microtubules in neurons might support quantum coherence, and that quantum entanglement might play a role in neural processing. If true, this would be remarkable, suggesting that the strange features of quantum mechanics might be relevant not just to atoms and molecules, but to the functioning of consciousness itself. However, these proposals remain speculative and controversial, facing challenges from the warm, wet environment of biological systems, where decoherence would be expected to be rapid. Beyond consciousness, quantum mechanics raises questions about realism, the view that there is an objective reality independent of observation. Quantum mechanics challenges naive realism, the idea that objects have all their properties at all times, regardless of measurement. At minimum, quantum mechanics shows that some properties are contextual, depending on what measurements are made. Whether this undermines realism entirely or just requires a more sophisticated realism remains debated. Some philosophers have suggested that quantum mechanics supports idealism, the view that reality is fundamentally mental or experiential. If observation brings properties into existence, if consciousness plays a role in collapsing wave functions, perhaps reality is not mind-independent after all. But this remains a minority view, and most physicists and philosophers of physics maintain some form of realism, even if quantum mechanics forces modifications to classical realist assumptions. There is also the question of what quantum mechanics tells us about causation. Classical physics describes a world of causes and effects unfolding according to deterministic laws. Quantum mechanics introduces probabilistic causation, where causes do not determine effects with certainty, but only make them more or less likely. Is this a fundamental feature of causation, or is it merely a limitation of our description? Entanglement raises even stranger questions about causation. When measuring one entangled particle instantaneously determines the state of another distant particle, is there a causal connection? It cannot be ordinary causation, because no signal travels between them. Yet there is a correlation that cannot be explained by common causes in the past if we take quantum mechanics seriously. This has led to discussions of non-local causation, backward causation, and other exotic possibilities. As we consider these philosophical implications, it is important to remember that they remain open questions. Quantum mechanics provides empirical data and mathematical structure, but it does not come with a built-in metaphysics. Different philosophical views can accommodate the quantum formalism, and choosing between them requires philosophical arguments, not just experimental results. This might seem frustrating. We want science to give us definite answers about the nature of reality, but perhaps the situation is actually healthy. Physics tells us how nature behaves. Philosophy explores what that behavior means. The two disciplines are complementary, and quantum mechanics, in its strangeness and its success, provides rich material for both. As we near the end of our journey through quantum concepts, let us reflect on the overall picture that emerges. Quantum mechanics describes a reality that is more subtle, more interconnected, more resistant to simple description than the classical world of everyday experience. At small scales, definiteness gives way to probability, independence gives way to entanglement, predictability gives way to fundamental uncertainty. Wave and particle, complementary aspects of a deeper reality, replace the simple objects of classical physics. And yet, from these strange quantum foundations, the familiar classical world emerges. Through decoherence and averaging over vast numbers of particles, the quantum uncertainty washes out, leaving definite, predictable, separable objects. The chair you sit on, the air you breathe, the light that illuminates your room, all are quantum systems at base, but their quantum nature is hidden beneath layers of classical appearance. This emergence is itself a deep question. Why does a classical world emerge from quantum foundations? Is classicality merely an approximation that works well at large scales? Or is there something more fundamental about the quantum to classical transition? These questions connect to interpretational issues about measurement and collapse, and they remain active areas of research. What is clear is that quantum mechanics has fundamentally changed our understanding of nature. Before quantum mechanics, physics aspired to reveal the clockwork behind appearances. After quantum mechanics, we know that nature, at its foundations, is not clockwork. It is something stranger, fluid, probabilistic, holistic in ways that defy separation into independent parts. This strangeness is not a defect. It is not a sign that quantum mechanics is wrong or incomplete, though the search for deeper theories continues. It is simply the way nature is. The universe is under no obligation to match our intuitions. Our intuitions evolved to help us survive in a world of medium-sized objects moving at moderate speeds. They were not shaped by evolutionary pressures to understand atoms and photons. That we can understand quantum mechanics at all, that we can write down its equations and verify its predictions, that we can build technologies based on quantum principles, this is remarkable. It speaks to the power of mathematics and experiment working together, of human curiosity pushing past intuition to discover truths that pure reason alone could never have reached. And there is beauty in this. The equations of quantum mechanics are elegant. The experimental confirmations are precise. The technologies we have built are transformative. From transistors to lasers, from MRI machines to atomic clocks, quantum mechanics undergirds modern civilization. Its practical success is matched by its conceptual profundity. As you rest in these final moments, as these words draw towards silence, let the ideas settle gently into your thoughts. You have descended through scales of size, from tables to atoms to electrons to quarks. You have encountered uncertainty not as ignorance, but as a fundamental limit built into nature. You have seen particles that are also waves, entities that defy classical categorization. You have glimpsed entanglement, the strange connection that links separated particles in ways that transcend space. And you have considered what all this might mean. how quantum mechanics challenges our concepts of reality, knowledge, causation, and determinism. These are not questions with final answers, but they are questions worth pondering, questions that connect the equations of physics to the deepest concerns of philosophy. The quantum world is strange, but it is our world. It is the foundation of everything you can touch, everything you can see, everything that exists in the physical universe. The strangeness is not elsewhere. It is here, in the atoms of your body, in the light entering your eyes, in the chemical processes of your thoughts. And perhaps there is something appropriate about ending our exploration here, in a place of openness rather than closure. Quantum mechanics has been developed over a century by thousands of physicists. It has been tested in countless experiments. It has been applied in ways its founders could never have imagined. And still, it remains in important ways mysterious, still open to interpretation, still pointing toward questions we have not yet answered. This is the nature of deep understanding. It does not remove mystery, but reveals new layers of it. Each answer breeds new questions. Each solved problem opens doors to unsolved ones. Quantum mechanics has given us extraordinary predictive power and technological capability, but it has not given us certainty about what reality ultimately is. And perhaps that is fitting for a universe that is, at its quantum heart, inherently uncertain. We have learned to calculate probabilities with astonishing precision, to manipulate quantum states with delicate control, to harness quantum effects for practical purposes. But the ultimate nature of the quantum, whether waves are real, whether particles exist when unobserved, whether many worlds branch off at each measurement, these questions remain open, inviting each generation to think them through anew. As this lecture comes to its close, as your thoughts perhaps begin to drift towards sleep, carry with you this sense of the quantum world, stranger than we imagine, more subtle than our everyday concepts can capture, but knowable through mathematics and experiment. It is a world where the act of looking changes what is seen, where distant things remain connected, where futures are probable rather than certain, where reality itself seems to resist final, definite description. The quantum realm is the foundation of everything, hidden in plain sight, operating according to rules that defy common sense, but describe nature with extraordinary accuracy. It is a testament to human curiosity that we have discovered these rules, to human ingenuity that we have learned to use them, and to human wisdom that we recognize there is more to understand. Let these thoughts rest in your mind as you rest. The electrons in your brain, firing in patterns that create consciousness, are themselves quantum entities, subject to the same strange laws we have explored. You are, in a very real sense, a quantum system, complex beyond measure, but built from the same fundamental physics that governs photons and atoms. And now, as silence returns, as these words fade into the stillness of evening or the quiet of night, may you rest well, knowing that the universe is stranger and more wonderful than it appears, and that human understanding, though limited, has reached deep enough to glimpse some of that strangeness, that wonder, that beauty hidden in the quantum foundations of all that is. Sleep well, in a universe that is, at its deepest level, not fully determinate, not entirely separable, not wholly predictable, but remarkably knowable in its patterns and probabilities. Sleep well in a quantum world. Sleep well